So in this video, we're going to continue with orthogonal matrices, and this time I'm going to talk mostly about orthogonal transformations. So quick review from the last video, we talked about orthogonal matrices, and the main definition here, well, the definition of an orthogonal matrix is that A is an orthogonal matrix if A inverse equals A transpose. And then we also talked in the last video about three different things that are all equivalent. So if you know one of them, you know the others. So A is orthogonal. Basically, you have an orthogonal matrix if that's true. And then it's also, remember, the column vectors of A form an orthonormal set. So the column vectors are orthogonal to each other, and they're all unit vectors. Or you can do the same thing instead with the row vectors. Now remember, to prove something's an orthogonal matrix, you don't have to prove all three properties. You just prove one of them, any one, and it implies the other two. And we proved that at some point in class. So then there's transformations. Remember, transformations, the way that we've talked about them, are when you take some vector and you plug it into a function, t, a transformation or a mapping, and then you get some new vector out of it. And I think we were calling it in class b. And really the way that you can represent this transformation is with matrix multiplication, A times U. And then that would equal B in this case. So, and then if we say T goes from Rn to Rm, then U, right here, U has to be in Rn, and B has to be in Rm. Okay. And if A happens to be an orthogonal matrix, then the transformation is called an orthogonal transformation. So that's this part right here, orthogonal transformation, where A is an orthogonal matrix. So it's really just a matrix transformation, and A is that special matrix. Now we'll talk about this part down here in a second. There are three main properties. There's a reason that orthogonal transformations are nice to study, and it's because of these various properties that you get. If you have some vector U in Rn, and then you plug it into your transformation in R, and you get a vector in Rm, then the two vectors have the same length, the original and the resulting vector. Or if you plug in two vectors, well, the angle that was between them originally is the same size as the angle that's between their new vectors, the image vectors. And then P and Q are these ideas here. If I have like U here and V here, and this point at the end is P, and this point at the end is Q, then the distance between P and Q is the same as wherever the distance ends up between T of U and T of V. So, like, I think, what do we say here? R and S. So the distance between P and Q right here ends up being exactly the same as the distance between R and S. The angle part says that this angle between U and V is going to be exactly the same as that angle between the images. And this length right here turns out to be the same as its image, and V's length turns out to be the same as its image, as long as that matrix A is an orthogonal matrix. So what I want to do here is actually prove some of this stuff. And before we prove it, so this is also in Rn, and this is in Rm. So before we prove it, I want to review a homework problem from, I don't even know how long ago, since I don't know when you're going to watch this video. So there's a homework problem, let's see, it was 7.1, number 3, and that said, let U equal a column vector, U1 down to Un, and V also equals a similar column vector. And we wanted to show that U dot V equal the same thing as V transpose times U. Okay, and quick, this isn't that long to prove, so we'll do it quickly. So first let's take U dot V. So that's the same thing as U1 V1 plus dot 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 plus UNVN. And that's pretty easy to show. In fact, there's not really any work to show. V transpose U is going to be the V vector transposed times U. Now, not dot U, just times U. And the reason we can do that, okay, the reason we can say just times is because if I turn the V vector sideways, so I take its transpose, it becomes a row vector that is 1 row by n columns, and then I'm multiplying it by a column vector, u1 dot 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 un, and that's an n by 1 matrix. And so I'm supposed to end up with a 1 by 1 matrix, which is really just a single number, and that number is going to be v1 times u1 plus dot 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 plus vn times un, and that number ends up being the same thing as u1 v1 plus dot 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 plus un vn, and that's the same thing as u dot v. Okay, so there's what we have. So let's now take a look at some of these properties that we mentioned up here. There's going to be one other thing that I'm going to prove first. So we'll start with, all of these are going to start with let A be an orthogonal matrix. So that means that A inverse equals A transpose. That's always given here. So the first thing we're going to do is notice this. So if I take, so here, let's redefine the transformation. If I plug in U into my transformation, that's the same thing as just multiplying by A, okay? And so what I want to look at is what happens if I take AU dot AV, where U and V are vectors in Rn. Okay, so that's the same thing. This thing right here is the same thing as saying T of U dot T of V, right? It's really no different. Well, let's use properties of the dot product. So using the property up here, instead of U and V, I'm doing AU and AV, then I know this should turn into the second vector transposed times the first vector. Okay. So and then we also know that now I'm going to interpret A and V both as matrices, and I know that when I have this property, I'll put this over here in a little bubble. Remember, we learned that if you have AB transpose, that turns into B transpose A transpose. So AV transpose right here is going to turn into V transpose A transpose, and then I've got AU next to it. And now I'm going to use the property of orthogonal matrices and change that V transpose, or the A transpose, into A inverse. And A inverse times A is just the identity matrix, so I'm really just left with V transpose U. And from part 1 up here, we know that's the same thing as just U dot V. So now we've got that, here, let me rewrite this, AU dot AV is really the same thing as U dot V. So the conclusion that we can make out of this thing is that orthogonal transformations preserve, that's the way you say it, transformations, preserve the dot product. Okay, So if you know A is an orthogonal matrix, then AU dot AV is the same thing as just U dot V. Okay? There are other ways of doing this too if you wanted to, but I don't know if you remember. Actually, we haven't done it with matrices, so that's the way we're gonna prove it. Okay, so now that we have this property, so I'm gonna highlight this. Let's take a look at some other stuff. So 2. Now let's look at the norms. So up here, we're going to try and prove these two guys are the same thing. So what I'm going to do is I'm going to start with this side. Okay. So magnitude of t of u. So that's the same thing as the magnitude of a times u, right? Because that's how I'm defining my transformation. And A is an orthogonal matrix. Okay. So that I don't have to deal with a bunch of square roots, let's just square these. And then I know that AU, the magnitude of that squared, is really AU dot AU. Whoops, no parentheses there. And I now know from part 1 that AU dot AV is the same as U dot V. So this is really the same thing as U dot U. And that's really the same thing as the magnitude of U squared. So now I've got that this squared equals this squared. They're both positive values squared because they're magnitudes. So then I can say, all right, well then T of U equal the magnitude of T of U equals the magnitude of U. Or you could say, some people prefer just the A version instead, AU equals U. Right? So this is a big conclusion here. So now we can say this idea is orthogonal matrix or orthogonal transformations preserve length, which is the idea that we talked about here. U and V have the same length as T of U and T of V respectively, as long as that transformation is an orthogonal transformation. Okay, so that's 2. And remember, this is still based off the fact that A equals A, or A transpose equals A inverse, because this property is based off of that. Okay, 3. Let's look at the angle between two vectors. So we know that the angle, so let's take U and V. So angle between two vectors U and V. So remember the cosine theta rule equals U dot V over magnitude U magnitude V. So the angle theta is really going to be the cos inverse of U dot V over the magnitude of U times the magnitude of V. And we know from number 1 and number 2 above here, let me highlight this one. I'll use this different color. So we know that U dot V, so I'm just going to change the inside here. U dot V is really the same thing as AU dot AV. So this is AU dot AV over, and then I know that the magnitude of U is the same as the magnitude of AU. And so I can use the same logic to say magnitude of V is the same as magnitude of AV. And this thing is really the angle between AU and AV, or between T of U and T of V, depending on how you want to refer to it. So now we've proven that that these angles have to be the same. So we can say, therefore, orthogonal transformations preserve angles. And that's the idea up here. Where is it? There it is. Where this angle right here between U and V has to be the same as this angle between TU and TV. Okay, we got one more to go. So that is the distance between two vectors, or distance between 2 points. So the distance between P and Q, and the distance between R and S. So actually, let me do this. Here, I'll draw a sample here. So here's U, here's V, and then let's say the TU is, I don't know, TU and TV. And so this one is P, this endpoint's Q, this one's R, this one's S. And we're supposed to show that this length is the same as this length as long as T is defined by an orthogonal matrix. So we can do this a few different ways, but the way that I think is simple, or one of the ways that I think is simple, is this length right here. If I made this vector, that's really the vector u minus v. So this length is the vector norm of u minus v. And then similarly, this vector would be the norm of t of u minus t of v. Now you could also do this whole thing by using the law of cosines, actually, if you wanted to, or SAS triangles from regular geometry or honors geometry. But let's do it using the stuff that we've been practicing in class anyway. So the distance here, let me write this over here. So the distance between, let's look at R and S, because that's going to use the uglier terms. So the distance between R and S is really the magnitude of TU minus TV, T of V, which is really the magnitude of AU minus AV. And that is the same thing as the square root of this vector, AU minus AV, dot itself. And then if I do a little dot product distribution using the rules that we know, then we're going to get AU dot AU minus AU dot AV minus AV dot AU. And remember, these guys end up being the same thing, and they're both minus, so it's really minus 2 of them. And then minus AV, or plus, sorry, AV dot AV. And so then this turns into the norm of AU squared minus 2 AU dot AV plus the norm of AV squared. And then we know that AU has the same magnitude as just U, which we proved just above here. So this is really magnitude of U squared. This is really 2 AU dot AV is really just U dot V, which we proved earlier, because orthogonal transformations preserve dot product. And then right here, this has to be V squared. Okay. Now, you can actually, if we looked at the distance between P and Q, these calculations are quicker. It's, it's the magnitude of U minus V, which is U minus V dot U minus V. And so then that ends up being U dot U minus U dot V plus, minus V dot U plus V dot V. And then we know that this is the same thing as magnitude of U squared minus 2 U dot V plus magnitude of V squared. And these guys are the same. Really, if you wanted to prove D of PQ equals D of RS, then you would have to go kind of in order. Like this would be, you know, you'd start here, and then you work your way down like this. And then once you get to this step, then you work your way back up to here, and then you end here. And so then we've shown that the two of them are equal. Okay, so I hope that helps some. In the homework, there are a couple problems that just ask you to kind of here's an orthogonal matrix, prove it's an orthogonal matrix, take these couple of points and do some stuff with them, and then show that it preserves all these things with your final answers and compare them to the originals. So it's pretty straightforward, I think. Hopefully it'll make sense, and we'll go over them again when we're all in class together. Okay,